Hi, my name is Stefanos Laskaridis and I will present you our joint work with my colleagues at Samsung AI Centre in Cambridge, UK on synergistic progressive inference. Up until now, the ML inference computational landscape has looked like this. On the one side of the spectrum, there is full on-device inference, where all nodes of a DNN are computed on the user's device. On the other end, there is full offloading, where the device is sending its data to a remote end, be it on the cloud or edge, where the inference is happening, and the result is returned back to the user's device with the privacy implications. Last, in between, there is partial offloading, where the DNN is split between device and cloud. In our work, we take this paradigm and enhance it with early exit networks, which are networks that can exit early during inference on easier examples. Apart from the obvious latency gains, this paradigm offers the benefit of being able to support devices of different capabilities with one architecture, as well as having at least one local actionable result in the case of remote unavailability. SPINN can act as an enabler of real-time and latency-critical applications. Moreover, it can offer robustness under spotty network connectivity and support a heterogeneous ecosystem of devices with one adaptive network architecture. Last, it can lead to significant cloud cost benefits as a result of early exiting. Here, we depict the general architecture of our framework, called SPINN, consisting of several offline and runtime components. However, let me illustrate SPINN's operation through an example. This is a ResNet block. Let's go through an inference example together. First, the input sample is going through the main backbone of the network. When it encounters an early classifier, it goes through its layers, while the rest of the computation continues. When the partition point between device and cloud is met, the client prepares the dependencies to transmit, and by employing our communication optimizer, it quantizes and compresses the activations before sending them to the remote end. Next, the server does the inverse, injects the dependencies back to the network, and continues the inference, going through the backbone and early exits as usual, potentially until the end of the network is reached. However, if, for example, an early exit is confident enough about the result, measured through the softmax probability of the classifier, it can stop the rest of the computation and communication, if need be, with the respective latency and resources gains. During runtime, the inference pipeline is coordinated by SPINN's scheduler, which takes into account the execution context, for example, network or computational load, as well as user-defined criteria, such as latency or accuracy SLAs, and decides on two policies. The first one is the early exit policy, which is the confidence threshold that we compare against to stop the inference early. This affects the distribution of samples exiting early based on how easily the example can be classified. The second is the partition point of the DNN, which divides the computation of the network between device and cloud. Next, I will briefly present the results of our evaluation measured across different deep neural networks and datasets on an NVIDIA Jetson Xavier with different energy profiles. First, we evaluated the throughput of our system under varying conditions, such as the available network bandwidth and the server load, as well as under user-defined SLAs. The key takeaways are that SPINN is able to consistently beat the baselines even under tough latency deadlines and adapt its policies to varying contextual factors without sacrificing accuracy. Next, we evaluated the robustness of our system to remote end disconnections. Over two scenarios and different failure probabilities, SPINN is able to achieve higher accuracy or lower latency over non-progressive offloading baselines, since it always has one or more local results to fall back on. Last, we measured the overheads of our system in terms of the scheduler invocation and the energy consumption of the user's device. The scheduler can adapt to varying conditions depicted by the similar trajectory of the first and last plots of the leftmost graph, with minimal overhead, since it does not have to be continuously invoked, while the energy consumed during inference is on par with device-only execution without early exits. In summary, we have presented SPINN, a distributed progressive inference framework, whose design, scheduler, and communication optimizer enable it to deliver higher performance than state-of-the-art works without sacrificing the system's accuracy or availability. Thank you for your attention, and I'm looking forward to your questions in the Q&A session.